we talked about buffers, right? We talked about Henderson-Hasselbalch. We talked about a little bit about buffering capacity, right? Buffering capacity in terms of how much change it can handle and what the concentrations are. They absorb large amounts of protons or hydroxide with small changes in pH. And that's kind of the whole point, right? They have the ability to absorb a whole bunch of hydroxide or hydrogen ion so that it can maintain the pH at the range that you need it. You know, like in the case of blood, we've talked about there's only like a 0.2 change, you know, between 7.2, 7.4. You don't want it to go much higher or much lower because that obviously affects the functioning of the entire organism. And the same thing with reactions, right? Reactions that take place at certain pHs. If the change happens, then obviously you're going to have a different reaction or one that possibly you don't want. Okay? And that is obviously determined by also magnitude of the acid and the conjugate base of the acid. Did you have a question?
No.
Okay. All right, so if we add a strong acid to something that's already buffered, okay, so what would happen? Well, let's look at something like hydrochloric acid with acetate and sodium acetate, okay, acetic acid and acetate. And it says, calculate the change that occurs if you had 0.01 moles of gaseous HCl added to 1 liter of solution that contains acetic acid. Remember, acetic acid is a weak base, and the way that this is set up here, 5 molar of acetic acid with 5 molar of sodium acetate, that's your buffered solution, right? Now, you add a strong acid to this, it's going to shift, right? It's going to shift the pH. But how is that buffered solution going to handle 0.01 moles of hydrogen being dumped in, right? So think about 0.01 moles is a lot of hydrogen. But you have a solution that can hopefully take up some of that H. So how would you go about it? Well, you know Henderson-Hasselbalch, which states that pH is pKa plus the log of the acetate ion over acetic acid, which is the base over acid.
What's like the pKa? How do we find
Negative log of Ka.
Okay, so if they give you the Ka.
So it's negative log of the Ka that's given to you.
Okay.
Okay? And then this was each 5 molar,
It's
right?
acid over
So
base.
log of 1,
Wait, isn't it?
No, it's base over acid.
Base over acid?
Yeah.
base over acid. So the base is your conjugate base, so that's your acetate ion. And in this case, acetic acid is your acid.
And pKa is negative log.
pKa is negative log Ka. And Ka is given to you, right?
You do negative log.
It tells you Ka of acetic acid is 1.8 times 10 to the negative 5. So pH is really the pKa of the negative log of Ka, which gives you 4.74. Okay? That's your initial pH. Right? Because it tells you you have 0.01 moles of gaseous HCl being dumped into 1 liter of this solution. Okay. So now what's going to happen?
So to find the initial, you just do the negative. You just do pKa, or do you need the pKa plus the log of?
It's the same. The concentration of the acid and the base were the same,
So
right?
then-
Originally.
Okay.
So it was log of 1. So that doesn't count, right? So then you just have negative log of the Ka as your pH. Okay. So then you're going to dump a whole bunch of H pluses in there. What's going to happen to the H pluses?
Wait,
What's going to take up the H plus?
Water.
The acetate,
Oh, the acid.
right? Because you have acetate, 5 molar acetate in solution, right? 5 molar acetic acid, 5 molar acetate. So you're going to dump a whole bunch of hydrogen ion, and hydrogen ion is going to be picked up by the acetate ion.
what about the chloride?
Chloride doesn't matter. Sodium can pick it up. It's not going to do anything though. It's not going to change pH. You're worried about pH at the moment, right?
Okay, yeah.
Okay. So you assume, and this is the assumption you make for all these reactions, that when the H is picked up, it's the reaction that happens, like the H plus the acetate, runs to completion, meaning it makes all of the acetic acid. So then, if that's the case, here's what's going to happen. Before the reaction, you're going to have 0.01 molar H. That's given to you. It said 0.01 moles in 1 liter, which is 0.01 molar, right? The acetate, you start with 5 molar. Once the reaction is done, you've added that much H to the acetate. So 5.01 molar is your acetic acid, 4.99 is your acetate. Okay? Now you have a new concentration of the base and the acid, right? 4.99 and 5.01. Even though you added this very strong acid, what happened to the pH?
It stayed the same.
Stayed the same.
Because it's buffered.
Exactly. So the ability of a buffered solution to pick up the H, right, its capacity to pick up that H is high enough that it really didn't drop the pH all of a sudden. Because if you think of 0.01 molar hydrogen ions, what's the pH of a 0.01 molar hydrochloric acid by itself?
1. No, what is it? 1. The hydrochloric.
2,
Yeah.
right? So 0.01 molar hydrochloric acid, pure 0.01 molar hydrochloric acid has a pH of 2. How do you calculate that?
What's the 1 times?
The negative log of 0.01, which is 1 times 10 to the negative 2, which makes pH 2. So you're dumping pH of 2 into a solution that has 4.74 pH originally,
That doesn't change.
and it's staying at 4.74. Does that make sense?
Yeah.
Because it's able to pick up the...
Right, exactly.
Which
So it has this amazing buffering capacity, right? It has this ability to pick up the proton and not allow the pH to drop.
Which one's
So
the
isn't
buffer?
that result of the buffer?
The buffering solution is your acetate ion with your acetic acid.
Isn't that a result of like the buffer solution with the acidic solution and the sodium acetate?
Right, exactly. That's your buffered solution. Okay? So optimal buffering occurs when you have HA and A minus equal to each other, because then your pH and pKa are really what it is. And so let's look at this. I think this was the problem that I wanted you to look at to do the review questions, right? A chemist needs a solution buffered at pH of 4.30 and can choose from the following acids and their sodium salts. Right, so you have chloroacetic with a Ka of 1.35 times 10 to the negative 3, propanoic 1.3 times 10 to the negative 5, benzoic acid 6.4 times 10 to the negative 5, and hypochlorous acid, which is HClO, 3.5 times 10 to the negative 8. So, which one would you use? In other words, if you had a ratio of HA and A minus to be log of 1, right? So the same concentration. Your pH would be based on what?
The pKa.
Right? Yeah.
It says in the what's it called, the actual problem that you can choose from your sodium counterpart.
The salt.
Yeah, so
So when you have an acid and it's salt, that's your buffer, right?
need to be sodium.
It can be really anything that's soluble. It can be potassium. It can be whatever. It's as long as it's soluble. Okay. All right. So what would you do? Well, you know that you want pH to be 4.3, which means hydrogen ion concentration should be 5 times 10 to the negative 5, right? And you want HA over A times Ka to be that. So
you do the negative log of all those options?
basically, what you want, right, is something that's going to give you the H plus concentration of 5 times 10 to the negative 5,
And they give you that.
right? Now,
They give you the 5 times.
they give you here are your Kas, right? Here are your ratios,
Mm-hmm.
okay? Which one would you really use?
0.78.
Why?
Because it's closer to 1.
Right. So you want a ratio where they're pretty much equal to each other. So you would probably use benzoic acid, because if that's the case, right? Because if that's the case, the benzoic acid and its sodium salt will be your best choice, because that's when you have a ratio of 1. And ratio of 1 gives you then your pH to equal to your pKa.
Can you go back to the chart?
Let's go back to the solution. Okay? First, let's go back to the problem. So, you have you want a buffered solution pH of 4.30,
Wait, but
right?
yes.
These are your options. You got 4 options with 4 Kas. Okay? Alright.
The salts just refer to the soluble.
The acetate of the sodium of the ion, anion. So you're going to calculate the ratio required to yield the 4.30, right? So, what do you know about your hydrogen ion concentration? Well, your hydrogen ion concentration is 10 to the power of negative pH. pH happens to be 4.30 because it's telling you that's what they want, right? And so when you take the quote-unquote anti-log, which is really just an exponent, right, to the opposite sign, you're going to end up with a hydrogen ion concentration of 5 times 10 to the negative 5 molar.
Why can't you use the Henderson?
You are.
But they're like, why
They're not
can't you
changing
just
it, they're just removing the P's.
So can't you just use the pH though?
You can. And that's what you're doing, but you want a ratio,
But
right? You need a ratio.
once you get the same
so
exact
you get
thing.
the 5.0 times
You want the
10 to the
ratio.
negative 5 from
So
the
you know that
AG.
pH is equal to pKa plus log of base over acid, right?
Yeah.
So basically you're getting rid of that concept of the logs and the P's, and you're just saying, okay, the concentration of H would be your Ka times your ratio, right? So at what point would your ratio be close to 1
Isn't it the other one?
based on the hydrogen ion concentration?
How do you get the ratio? How do you get 3.7 times 10 to the negative 2?
They divided
Plug
the
in.
5.0.
5 times 10 to the negative 5 divided by 1.35 times 10 to the negative 3, you get 3.7 times 10 to the negative 2. Yeah.
Oh.
The pH is-
In the Henderson Hasselbalch, that one,
Mhm.
the equation, it was,
And pH is equal to pKa plus log of A minus over HA.
yes.
When you take all the P's and the logs out,
No,
rearrange
I'm
the
talking about
formula, it
ratio.
ends up being this.
The ratio. So the,
Rearrangement is this,
okay.
right?
Can I'm gonna say it.
I don't know if this is I'm just gonna ask. If we wanted the pH of 4.3,
pH is 4.30, given to you.
You take the and
You are getting the hydrogen ion concentration from pH.
but it wants to stay at that pH, right?
Yes.
But then if the
How is it going to stay at that pH?
if the ratio is 1,
Closest to what?
but if the Ka equals the pH, then do you get what I'm saying?
If this is 1,
Yeah.
then pH and pKa are equal to each other, right?
But if the pKa of whatever is 6.4, then isn't that not 4.3?
Oh, I get what they're doing, so you don't have to do
Yeah,
the
but you do
anti-log.
5.0 divided by
Yeah, but that's the
6.4.
really, if you look at it, because ignore everything else, which one of them, ignoring everything else, think about it.
Yeah.
Which one is closest to 5 times 10 to the negative 5? That's really what you're looking for.
Oh, because that's what the pH is? Okay.
Because that would give you this.
That would give you a ratio of 1, close to 1,
So if
which
you
would
were
allow you
doing-
to do that.
If I'm doing the equation thing, and then I get to the point where it's 1 point something equals the log of the base over the acid,
Mm-hmm.
would I take the anti-log of?
Yeah.
I would. Let me see if that works.
I think
Because if it's,
it's a plus log, but it's pH and
but then it's negative that over that. But if I just want the ratio and I want to get rid of the log,
you gotta do 10 to the exponent, don't you?
Do E.
Not E. E is natural log. This is log base 10. Alright, so pKa for benzoic acid is 4.19, which is about 4.3.
Did you track it from your direction too?
She was like,
Took her an hour and 30 minutes to get to school.
Alright, so titration, what you guys don't love so much, but those of you who've done titration, you're not so crazy about it, but you'll see it's really not that bad.
we did it.
A little bit.
I haven't done it. It's okay.
Alright, so what is the purpose of titration? Purpose of titration is to determine an unknown solution of either an acid or a base by reacting it with either an acid or a base that you know the concentration of. Okay? And you use an indicator, a pH indicator, something that changes color. Remember the equilibrium lab you guys did on Sunday, right? Things changed color, like it went yellow, blue, whatever. Okay. Those are indicators, like the bromothymol blue is a pH indicator. And there are different indicators that change color at different pHs. So you know that your titration has come to an endpoint. And we'll look at all that. Okay. Then you graph it, bless you. Then you graph it to determine exactly what your endpoint, your midpoint, your equivalence point, all that good stuff is. Okay? You with me?
Wait, endpoint, like, when...
Endpoint is when the reaction ends, when the color change happens.
So it's a curve.
It's a curve. Yeah, you'll see where the endpoint of that curve is based on the equivalence point. The net ionic equation for a titration is really just a neutralization reaction, but depending on what kind of acid and what kind of base you're using, neutralization reaction doesn't mean you're going to end up at pH of 7. If you have a strong acid with a strong base, your pH of 7 is pretty much your endpoint. Okay? But if you don't have a strong acid and a strong base, let's say you have a strong acid and a weak base, your endpoint will be less than 7, right? Because the stronger acid is going to weigh more.
What if you have weak both?
If you have weak both, then it's going to probably be above, usually above 7. Okay? So, and again, the purpose of this is to determine the hydrogen at a given point in the titration, determining amount of it remaining at that point, and so on. And we'll see how this works once we see the graphs in a minute. One of the units you're going to use for titration is a millimole. It's moles, right? And millimoles is just basically 1,000th of a mole. So if you divide millimole by milliliter, it's still the same molarity.
Oh, that makes sense.
Okay, because you're dividing 1,000th by 1,000, so you're kind of canceling out the thousands in a way, right?
So when so if he gives me
Because you're dealing with usually tiny numbers and milliliters of volume. That's why you deal with millimoles instead of moles.
But it kind of ends up being the same.
But in all reality, you can do either way.
Either moles and liters or millimoles and milliliters.
Mm-hmm. Exactly. Okay. So, it says consider the titration of, you have 50 milliliters of 0.2 molar HNO3, and you want to titrate it with 0.1 molar of NaOH. When you don't have any hydroxide in there yet, you have your H, you have your water, and you have your NO3 minus, right? And you have, that means you have 0.2 molar HNO3, which means you have 0.2 moles of H plus. If you have 0.2 moles of H plus, what's your pH? How do you find pH from this concentration of hydrogen?
Isn't it 1?
What do you do?
log.
Negative log. So you plug in negative log 0.2 and your calculator is going to spit out 0.699. Okay?
Is there a way to figure that out without a calculator?
Not if the base is not a 1. If it's not a 1, no.
It's 0.699 or 6.99?
0.699. Less than 1. Pretty strong acid, right?
Yeah.
Okay. So if you add 10 milliliters of sodium hydroxide to this solution that you had already, right? So now let's look at what's happening. You had 0.2 molar H plus, right? 10 milliliter of 0.1. How many millimoles is that?
The 10.
10 liters of
10 milliliters of 0.1 molar,
It's 0.01.
right?
Oh no, that's the milliliter.
9.0.
So you have H plus, you have 50 mils, right, of 0.2, that's 10 millimole. How many millimoles is 10 mil of 0.1?
1.
1 millimole, right? So it's 0.1 times 1. So you have 1 millimole of hydroxide ion being dumped in. And what's going to happen to that hydroxide when you put 1 millimole of hydroxide into a solution that has 10 millimoles of H plus?
0.
It's gonna add.
Okay, think about what you're saying before you say it. So you have H plus, right? You got 10 millimoles of it. You add into this solution hydroxide ion of 1 millimole. What is this hydroxide going to do with this H plus?
H2O.
Okay, so that means it's doing what from this? What does the 10 become? What does it become?
9.
9. Why?
Because it subtracts the 1.
Why?
Because it gives the H to OH.
You're taking 1 millimole of H plus to bond with your 1 millimole of OH minus.
Make 1
So at the end, do you have any OH minus left?
No.
When will you have OH minus left? How much OH minus do you have to add to this solution to end up with more OH minus? More than what?
1.
More than what?
10.
Yep. Until you get to 10 millimoles, will you have more hydroxide than hydrogen?
Yeah.
Right? So at 10, you have equal. But until then, it's going to take up, and this reaction is going to completion. H plus and OH minus together, they're not going to just kind of swim around and say, okay, we'll see you later. They're going to bond and make water. That's just what they're going to do. You're assuming this reaction is to completion. Okay?
Is that something you assume, or is that something they tell you to assume?
That's the assumption, is that most of these reactions are going to completion. So then, you already know it's the 9 millimoles left over. Now, the one thing you have to keep in mind is when you're adding hydroxide, now what's happening to your new volume? Increasing. So you have to now get the new concentration of H plus with the new volume. It's not just 9 millimoles over 50 milliliters anymore. It's 9 millimoles but over 60 mils, because you just added 10 milliliters of hydroxide solution. So now what do you have? 0.82. What was your pH originally?
0.699.
Okay. So pH is going to go up, right?
Can you stay on it for 1 more second?
Yeah. So now, tell me the math for 20 milliliters of hydroxide added.
So it's 9 over 70.
Not 9 anymore.
So
Can you repeat that?
right?
So if I add 10 more
19.
mil of hydroxide,
10
Would it
more
be
to
18?
that.
10 more mil of hydroxide, that means I'm adding 1 more millimole of hydroxide. What's going to happen to this? 8 millimole. What's going to happen to my volume?
It's gonna go 8 divided by 70.
Yep. 8 divided by 70. Now pH went up to 0.942. Okay?
How do you get from 0.11 m to pH?
Negative log.
Negative.
Concentration to pH is negative log. So, you keep on adding, you keep on adding, you keep on adding, right? And you'll get to a point where it says that when you add 50 mils, right, that's 5 millimolar, pH is 1.30. When you add 100 mils, then that's when you're going to have 10 millimolar of hydroxide added. Okay? So, the stoichiometric or equivalence point of the equation is where you have sodium, nitrate, and water. What happened to hydrogen and hydroxide here?
It disappeared.
At equivalence point, what do you have? Equal amount of H plus and OH minus. What's going to happen when you have equal amount of H plus and OH minus?
Water.
They come together and make water. Okay? And since nitrate and sodium have zero effect on the pH, right, because they're neither acidic nor basic, so they're not going to change pH in any way, pH at this point, you assume, should be 7. Strong acid, strong base, equivalence point is 7. Okay? Now, what if you added 150 mil of hydroxide? So now you have excess hydroxide in there, right? And excess hydroxide, right? Now you have 5 milliliters of extra hydroxide in 200 milliliter solution, right? Because you added a whole bunch, right? You added 150 milliliter of hydroxide to 50 mil of H, and you end up with 0.025 molar hydroxide, right? So now pH became 12.40.
You found out negative log?
Yep, always. So, you started with pH of 0.699. with a solution where you had no sodium hydroxide. You get to a pH of 7, that's your equivalence point. You keep on adding hydroxide, pH keeps on going up, and you're going to get to a pH where it's obviously way above 7. That's what the curve looks like. So you graph volume versus pH, and it's going to obviously level off somewhere.
Do we graph on our test?
Yeah,
Or just go with-
these are graphed by hand, just because
We've done that before.
a strong acid and a strong base
We did that
is
with
always
acid
going to look
base.
the same, because your equivalence point is always going to be a 7.
So the 9 divided by 50 that we just did, is that what that is, or is that a different graph?
Yeah, the pH of 0.699,
Uh-huh.
and then you keep on adding sodium hydroxide, pH keeps on going up. You see how it just shoots up here, right? Because you hit equivalence point, and then anything after that is just going straight to higher pH. It's really easy to miss equivalence point, by the way, when you do the titration lab. You have to do it several times before you get it right.
So we probably didn't. We probably didn't when we did ours. But we
We
didn't do
didn't
a
do
You
titration.
didn't do titration. You did equilibrium.
Did we do one last year?
Yeah, we did it last year.
Oh, last year, yeah.
What was that lab?
Titration. The one where you swirl, it turns pink, and then you put a few more drops, it turns pink, and then it gets to a point where it turns way dark pink where it shouldn't have.
Oh yeah.
So we look at the titration through the color.
You look at the equivalence point through the color. That's when you know you have to stop the reaction. Otherwise, how do you know
Yeah.
that you reach equivalence point? You don't. Because it's two clear solutions. Without the indicator, it's just two clear
You
solutions.
won't know.
You won't know. And we'll do a titration lab, by the way. So calculating H plus and pH before equivalence point, you have pH at equivalence point, and then you can calculate hydroxide after equivalence point, all from that curve. Okay? So what if you're titrating the other way around, meaning you start off with the strong base and you're adding strong acid? You're not going to start at the bottom anymore, are you? You're going to now start at the pH of the base, whatever that may be.
Okay.
So if you have 0.5 molar sodium hydroxide, right, 100 mils of it, and you get the pH of that, and it's going to be up there, and then now you're going to start adding hydrochloric acid? Yeah. You're going to start adding hydrochloric acid to it, and as you add hydrochloric acid, the pH is going to start dropping, as you can see on the curve, right? And then it's going to have this really
How do you
steep drop.
get the pH of it again? Can you, the 100 ml of 0.5 you would do?
So you have to find molarity, right?
So you would like
Would you do negative log of 0.5?
Negative log of your concentration, yes. Okay? So determining H plus, you can determine hydroxide, you can determine your equivalence point, and all that good stuff.
so you
Okay.
kind of ignore the 100 ml of it. You just do negative log of 0.5.
Yeah, that's your original pH.
And then when you do then you would do like the 80 divided by 70 part of it, like the.
That's when your volumes come in, because you convert all those to millimoles at that point. Okay? So if you have a weak acid with a strong base, so reaction of hydroxide with weak acid assumed to run to completion, because, well, the strong base is going to take up all the weak acid H pluses, right? So you're not going to have any H pluses left over. So it's going to be high pH. It is an equilibrium problem, because position of the weak acid equilibrium has to be determined for pH to be calculated. Remember, acids that are weak or bases that are weak are in equilibrium. Everything else is in completion. Okay. So now, knowing that, let's titrate something like hydrocyanic acid. Hydrogen cyanide gas is a powerful respiratory inhibitor and highly, highly toxic.
Yeah,
It is
I
a
want that.
very weak acid. When you dissolve the hydrogen cyanide gas in water, you're going to end up dissolving it, but you're going to have a Ka of 6.2 times 10 to the negative 10.
That's big.
So you don't really have a lot of H
You can
pluses,
take
do
that
you?
into, like, no.
Okay. But here's what's going to happen. You're going to take 50 ml sample of the 0.1 molar HCN, and you're going to titrate it with 0.1 molar NaOH. And you're going to calculate pH at 3 points. After 8 milliliters of this NaOH has been added to it, at the halfway point of titration, and at the equivalence point. How are you going to do that? Carefully. Okay, so 8 milliliters of 0.1 molar. First, let's think about what in the world your reaction is. You have HCN, right? You have hydroxide. HCN has HCN and hydroxide, and then you have cyanide and water. Okay? You start with 5 millimoles of HCN, right? Because it's 50 milliliters of 0.1 molar. And you're adding 8 mils of 0.1 molar NaOH, which is 0.8 millimoles, right? Again, millimoles make it easier to do the calculations because then you're dealing with just numbers like 0.8, 0.5, and all that stuff, versus otherwise you're going to have to deal with like 0.003, and it's going to be really annoying, and you're going to have a whole bunch of negative exponents, which nobody wants to deal with because you're more likely to make mistakes. That's why the conversion to millimoles, by the way. So, you start with 5 millimoles of HCN, you add 0.8 millimoles of OH minus, and now you have 4.20 moles of HCN. Okay? So the 4.20 moles of 4.2 millimoles of HCN is your initial, right? 0.8 millimoles is cyanide, and you don't have any H to begin with. At equilibrium, you have HCN, you have CN minus, and you have H plus. But how much of each do you have? So, 4.2 over 58, because it was 50 to begin with, you added 8 milliliters. Cyanide was 0.8 to begin with, and then you, again, divided by 58. And hydrogen, you don't have any in the beginning, because you started with HCN. So now the ice table looks like this. And I'm going to, again, assume that I start with initial hydrogen ion of 0. Okay, now you can plug in. You can go ahead and solve those numbers, or you can just plug in as it is and deal with it later. It doesn't matter, 0.8 over 58 and all that stuff. So you know Ka, you know what you're dealing with, and now you know that after you add 8 milliliters of sodium hydroxide, pH is already at 8.49.
So that's the beginning of it.
That's 8 milliliters of it added only. Okay? And given that it's such a weak acid, it makes sense that the sodium hydroxide is going to be the powerful one here, and that's why you have a pH higher than 7.
But, so that's so like in the graph, the titration.
That's just 8 milliliters, whatever the 8 is, right? The curve that looks like this. It's going to actually start high and then go low. At the halfway point, what is the halfway point?
Thingy with 7. Equivalence.
Halfway point, so you have 50 mil of 0.1 hydrogen cyanide, right? So you have 5 millimole. So then how much sodium hydroxide do you need for that 5 millimole?
Wouldn't it just be divided by 2?
2.5.
Yeah.
In order to get 2.5 millimoles of hydroxide, what volume do you need? 20. So, same idea of calculation, but now you're at 25 milliliters. Okay? So at the halfway point, HCN and CN minus are equal to each other, right? That's your assumption. So that means if you use Henderson-Hasselbalch, you know that the log of A minus over HA is really just a 1, right? And so pH is your pKa, which is 9.21. So at the halfway point, pH is 9.21. Okay? At the equivalence point,
So there's the halfway point and the equivalence
Yeah.
point.
at the equivalence point, the reaction that will control the pH involves the basic cyanide taking proton from water.
So the hydrogen ion, basically.
So now you have hydroxide in solution, right? And that's really just Kw over Ka. You already have Ka, so you're looking for Kb. Okay?
KW over K.
Okay? So, you know that you have 5 millimoles of this thing, the cyanide, and you added 100 mils, right? So you can do the equilibrium concentrations. Then you can plug it into Kb. When you do that, you see that pH ends up being 10.96. Okay, so that's the last one. So weak acid, strong base, equivalence points is affected by the amount of acid. pH of the equivalence point is dependent on the acid strength. And the strength of the weak acid affects the shape of the curve. The curve will look different. Weaker the acid, greater pH value at equivalence point. Okay, because then the base takes over.
Oh, yeah.
These are what the curves look like when you have a strong acid and when you have an acid and a base, right? So strong base, weak acid. You see how the weak acid starts at a pH that's around, let's say, 6 because the Ka is 10 to the negative 10, and that curve is not very big, right? That doesn't have that steep line going up. But when you're dealing with something like a strong acid, look where the pH is, like a 1. And as you're adding the strong base, remember that it's going to shoot up to this. And so it's going to look very different than this curve right here. Okay, so keep that in mind.
Isn't that a strong base or not a strong, like a weak base?
No, the base is strong. Look at what base you're dealing with. Sodium hydroxide. These are all your possible acids. The weak acid, the curve looks like that. Strong acid, curve looks like that. Okay, so you're going to have very different curves. Okay? All right.